the organizers asked me to intersperse this with my research journey. Uh, I, I want to focus more on the technical aspects of some recent work. Uh, so, like Meena mentioned, I was very fortunate to have Manindra Agarwal as my advisor when I started my research career. He already had an approach for a pretty old problem in algebraic number theory, in algorithmic number theory, and uh, he also played the most important role in solving it. Uh, but that early, uh, like accolades that we won for our work, that helped a lot. And my research career trajectory has been pretty unusual in that way. So it gave me the freedom to work on like very difficult problems in areas that I worked on. So, for example, for after primality, the next natural thing to try was factoring, integer factoring, and we worked on it for many months without making absolutely any progress. So, there have been a lot of these failures, but yeah, still the ability to fail or the opportunity to fail was very important. And I've had many wonderful mentors, Manindra, Avi, Eric, Sriram, and many wonderful collaborators, Ankit, Chandan, Ram Prasad, and some of this work is joint with Ankit, Chandan, Ram Prasad. So let me start. So I want to tell you a little bit about unsupervised learning, what we hope to do, some sort of holy grail of this area. What we so, for example, if we were to do unsupervised learning for vision, what we would get as input is a humongous collection, let's say almost the entire set of images and videos about the world that are available. And then we want to use them to understand our world. And there's a bit of a bummer here because we don't even know how to define or quantify understanding. And we have some tentative definitions. So let me not go into that, but at a very high level, what we are hypothesizing is that real world data sets like image and video data sets, they are some sort of iterated combination of some structural patterns, and I'm intentionally being vague here because I myself don't know what all the structural patterns there are, and some simple random distributions. But I will give examples, and what the rest of this talk will be about are solutions to some of these problems, sort of some special structural patterns and some random distributions for which we are able to do the learning. So let me give some examples of what I mean by structural patterns. So now, in the rest of this talk, I will abstract out my input as a collection of points in n-dimensional space. So, although for data sets like images and videos, really it should be thought of as collections of sets of points, and you have to do the encoding appropriately. But in the rest of this talk, my data is a collection of points like this, for example, right? And this particular collection of points has some nice structure to it, and I'm sure all of you would be able to see that visually what the structure is. So in this case, there are a small number of subspaces, and all my data points are close to one of these subspaces. In this case, these are lines in the plane, right? And what this problem, when generalized to n dimensions, is called subspace clustering. We are given a set of points in n-dimensional space, and we want to find a collection of low-dimensional subspaces such that all the given points are close to one of these subspaces. Yeah, if you have clarification questions, please feel free to interrupt me and ask me. So, let me give some examples of random distributions, some simple random distributions. So, here is another collection of points. It's mostly random, but the distribution from which it is picked is simple. So, in this case, it's a mixture of two Gaussian distributions in the plane. So, a Gaussian distribution is a generalization of the normal distribution to n dimensions, in this case 2 dimensions, and a mixture of Gaussians is the following kind of distribution. In this case, for example, it's a mixture of two Gaussians. So, here is how you would pick a point. Let's say you pick one of which distribution to choose with some probability, let's say half each, and then from that particular distribution you sample a point. And the problem here is, when we are given point sets like this, we want to identify what these two distributions are, learn the parameters of these two distributions. So, both these problems, subspace clustering and Gaussian mixtures, they have a long history. There's an enormous amount of work which has happened on both these problems, and I won't be able to even begin to summarize that work. So, sorry for that. I will be skipping references, but there has been a very significant development building on our work. Just like a couple of months ago, Aditya Bhaskara, Eric Evert, Srinivas Vedehi and Vijay Raghavan, they proved some of the conjectures that we had. We had an algorithm which I will talk about, and the correctness of the algorithm depended on some conjectures about singular values of certain matrices. So, they proved that conjecture, and also building on work by Mitali Bafna and a bunch of people. So, this almost resolves this mixture of Gaussians problem, which whose origins go back a long time ago. So, let me give some more examples where you have some sort of combination of structure and randomness. So, there is this problem called blind source separation. Here the problem is the following. Suppose you have, let's say in this case, 7 sources of sound and 7 receivers. So, 7 sources and 7 receivers, and what each receiver receives, the audio signal that it receives, is some linear combination of the audio signal emitted by each of the sources. So, what we want to do is to untangle these sources. So, we want to decompose it back into the original sources, the audio signal, the mixed signal, into the signal for each source. And yeah, the first time I saw this problem, it seemed very surprising to me that it can be solved. And the key here is that we assume that these sources are independent sources and that's an extremely powerful assumption. like it's natural but extremely powerful, and you can use that to separate out the sources. So more formally, we have, again, you can think of it as a set of points. So the sources are at each time step, the audios generated by the source, you can think of it as a point in 7-dimensional space, and the receiver, it receives again a point in 7-dimensional space at each time step. So then we are sampling this sources at various time steps. So we have a collection of points in 7-dimensional space, and assuming that the sources are independent, we want to recover this mixing matrix A. And there's a generalization of this to polynomials. Now the sources are, let's say, again, independent random sources, but the receivers, what they receive are polynomial functions of the source signals. And can you find these polynomials? Yeah. And so each received coordinate is a low degree polynomial in the sources. And it turns out that what I'm going to talk about, the ideas apply also to even modality which is different from even discrete data. So for example, there's this problem called topic modeling, where we are given sequences of words. So for example, like think of 4 sequences of 8 words here like this, and what we are told is that each of these sequences correspond to one specific topic, and we want to find out what those topics are. So in this case, the first and the third set of words correspond to, let's say, cricket. The first and the third correspond to vaccination and medicine, and second and fourth to cricket. And we would want to be able to automatically identify what these topics are. So, yeah, before I go on, any questions about these problems? So, let me give you some idea of how to proceed along for these sorts of problems. And this is where I'll build the connection to algebraic complexity. So, you have a set of points in n-dimensional space. What you can do is, you can look at what are called the empirical moments. So imagine sampling a random point from this set S that you are given, and so you can look at let's say the expected value of the first coordinate of the point, or the expected value of the square of the first coordinate, or the expected value of the product of the first and second coordinate. So these are called the moments. And the reason that we look at these objects is because for pretty much any reasonable distribution, the empirical moments will be very close to the true moment. So these samples, the way I get these samples, I sample a bunch of points from some distribution that I'm trying to understand. So imagine if instead of sampling this X from the given set S, I were to sample it from the original distribution, then for pretty much all reasonable distributions, and in our case, all, like I haven't defined it, but yeah, pretty much all distributions will be reasonable. So then these empirical moments will be very close to the true moments of the distribution. So we have uh, at least some starting handle on randomness. Okay. So now the next thing is, it turns out that if you think about it, in principle at least, from these empirical moments, or at least if you knew the true moments of the distribution, you ought to be able to recover the parameters of the distribution. So parameters are just, let's say for the Gaussian, it's the one-dimensional Gaussian has two parameters, the mean and the standard deviation. And similarly, the two-dimensional Gaussian has the centroid and some a 2 by 2 matrix of covariances, and so on. So we want to recover those parameters, and in principle you can recover it, but the question is how to do it efficiently. And here's what the connection to algebraic complexity comes. We are going to take these moments and put them as the coefficients of a polynomial f. So for example, I take the empirical moments and form a polynomial. Let's say I take the second order empirical moments and I form this quadratic polynomial where the coefficients of the quadratic monomials are essentially the corresponding empirical moments. So this is just a very nice bookkeeping device at this point. So it's something which, it's a nice bookkeeping nice way to track all the second order moments in this case. But then something remarkable happens. So in each of these cases that I showed you, this polynomial f tends to have a small arithmetic formula. It's the first time I saw this, that in so many different settings this happens to be true. It's quite surprising that this happens. So then this means that if you want to understand these distributions where the moment polynomial has a small formula, we want to be able to, given a polynomial f, find the small formula for it. And typically once you find the formula for it, you can just read out the parameters of the distribution very easily from the formula. So this is our plan. We will learn this formula for f and read out the structure. So yeah, this part will have quite a bit of intersection with Newton's talk yesterday. So I want to remind you a little bit about polynomials and formulas for polynomials. This is overlapping with Newton's talk yesterday. So we have polynomials which are objects like this, and we want to find small formulas for it. So formulas are like a more precise way of saying mathematical expressions. So, and as computer scientists, we think of mathematical expressions as trees. So this particular expression for this polynomial, I can think of it as a tree like this. It's a natural way of doing it. The nodes are addition and multiplication. Additions compute arbitrary linear combinations, which we sort of capture via weights on the edges, and the final output node outputs a polynomial. So in algebraic complexity, the main question is how many operations are needed to compute a given polynomial f. And yeah, I will give a slightly different example to motivate this problem than what Nutan gave yesterday. So consider a graph and we want to find Hamiltonian cycles in the graph. So the reason that I'm giving this example is you might remember that finding Hamiltonian cycles in graphs is an NP complete problem, and there's a natural way to capture this as a polynomial, as computation of a polynomial. So here's what you can do. Yeah, the Hamiltonian cycles essentially capture all of NP. So imagine a graph with a complete graph on n vertices where the edges are labeled by variables xij, and xij is, think of it as being either 0 or 1. 0 if that edge is absent in a given input graph, and 1 if that edge is present. So you can write down a polynomial which goes over, you sum over all possible Hamiltonian cycles in the complete graph, and for each such cycle you can have a monomial which is, as in this case, of the product of the variables on the edges of the cycle. So one summand here is 1 if that cycle is present and 0 otherwise. Yeah, the exact expression is not important, this property is important. And then when you sum up over all possible Hamiltonian cycles, it means that this polynomial has this property that if you give it an actual graph with so xij's are zeros or ones, then the value of this polynomial on the given input graph is precisely the number of Hamiltonian cycles in that graph. So this polynomial called the Hamiltonian polynomial has this property, and it turns out that this was the insight of Valiant which Nutan mentioned yesterday, that if this particular polynomial can be computed efficiently, then in some sense all combinatorial problems, all combinatorial counting problems can be solved efficiently. And yeah, there are stars here which, and in this talk I will often make informal statements which will, I won't specify all the technical things or the caveats. I will hide them under stars like this, just to give you a flavor of the result. So this is really remarkable, right? You solve this or you compute this one single polynomial, and essentially all combinatorial counting problems you would have found algorithms for. And so arithmetic complexity, people have always wondered, does this polynomial, or there are several such sort of what are called complete polynomials, do they have small formulas or not? And we still don't know the answer. This problem is called the VP versus VNP problem. And we conjecture no, almost nobody thinks the answer is the other way around. But if it were the other way around, we don't even consider that possibility among us. But if that were true, in particular, it would imply that P would be equal to NP, but not the other way around, like Nutan mentioned yesterday. So some years ago, again I'm cheating here, but some years ago, essentially we could prove lower bounds on formulas for Hamiltonian under some restriction that we were calling regularity, that the formula should essentially roughly be a balanced tree. And Small here is, as usual, polynomial size. And recently, Nutan, Shrikant Srinivasan and Sebastian Tavenas, they had this wonderful result, which was a stunning breakthrough in this area, that Hamiltonian does not have constant depth polynomial size formula. And that was one of the main results in Nutan's talk yesterday. So, so we have made some progress, and yeah, sometimes it seems we are quite close, but not yet there to resolving VP versus VNP. So yeah, it's much stronger in many different ways than our result. So what I want to tell you today is that you can use these lower bound proofs. There's some sort of template to use these lower bound proofs to get learning algorithms for some of the problems that I mentioned in the beginning. So I want to talk about that. Any questions? So in order to do that, I'll have to give you a quick overview of these lower bound proofs, how they go. So yeah, but sort of let me first mention some informal versions of the results that we'll see. What we showed was this, that you can use these lower bound proofs. In particular, these lower bound proofs use some linear maps, and those linear maps you can use to design efficient algorithms that, given a polynomial f, reconstruct small formulas for f, if they exist. Okay. But under mild non-degeneracy conditions. I forgot to mention one thing. So the problems that I mentioned in the beginning, in the worst case, all of them are NP hard. So there is no realistic hope of solving any of them in the worst case. If you give me adversarially chosen inputs, I cannot hope to solve any of those problems. So all these results, all the algorithmic results will assume some non-degeneracy condition, but the non-degeneracy condition or some conditions which will hold if you are to choose the input in some sense randomly. And in fact, we would want to prove even stronger thing, that even if you choose the input in the worst case fashion and perturb it slightly, even then these algorithms work and they give the correct output. So that's called smoothed complexity, and yeah, and that's what the most recent result was about. It proved the smoothed complexity of some of these problems. So in a follow-up work, what we showed was that even if you are given the polynomial approximately, so we are not, or think of it this way, that we are given a polynomial which is close in some sense to a polynomial which has a small formula, and then we want to recover that small formula. So close here would, you can think of it like this. Now think of the polynomial as a vector. So for example, if you have a quadratic polynomial in n variables, it's a vector in roughly n square by 2 dimensional space. So if you are given some polynomial which is close in the sense of Euclidean distance between polynomials, then can we recover the small formula for the polynomial if there's some polynomial in the neighborhood which has a small formula. That's the question. And again, there are caveats to this, but essentially we have a general sort of meta algorithm that will take a lower bound proof of the kind that we discovered or Newton discovered and turn it into a reconstruction algorithm for formulas. And it can also tolerate this noise or this approximation. And yeah, there's substantial cheating going on here, but in this slide. But essentially, this implies that as a corollary, you get a single algorithm which will solve all these different, seemingly very different problems in unsupervised learning. The cheating that is going on here is that there are non-degeneracy conditions involved, and we don't know in all these cases how to rigorously prove that those non-degeneracy conditions hold if you choose your input randomly. But yeah, so there are technical challenges to doing that, but roughly, any questions about this? So let me just hint what those technical challenges are. In trying to prove lower bounds, like Newton was saying yesterday, it boils down ultimately to proving ranks of certain matrices. And for proving bounds, you only need bounds on the ranks of certain matrices, upper and lower bounds on the ranks of certain matrices. But when you are trying to do reconstruction or learn a formula, in particular, you'll have to be able to distinguish a polynomial which has a formula of size 100 from a polynomial which has a formula of size 101. Like even a slight change of size, at the very least, your algorithm should be able to detect that. So what this implies is that in terms of those ranks of those matrices, is that you need to prove very precise on the nose rank bound for those matrices. Essentially, there's essentially no room for error. You have to get those ranks on the nose, and that turns out to be challenging in many of these situations. And then this recent result essentially is the following. Not only are they able to prove these rank bounds, but they're able to go even one step further. These matrices, so rank corresponds to how many singular values of a matrix are non-zero. So this most recent result, they show only not that these many singular values are non-zero, they can prove bounds on how small the smallest singular value will be. So yeah, it's amazing that they can do that, and that's why you get, as a corollary also, combined with those singular value bounds, smoothed algorithms for these problems. So I want to now give you some flavor of this connection between lower bounds and learning. How can you learn formulas using lower bound techniques? So here's a sort of an abstract problem. Suppose we are given a multivariate polynomial f, and suppose that it is approximately equal to a sum of simple polynomials. So here's an example to keep in mind. So by simple will mean low circuit complexity polynomials. So for example, each summand could be a power of a quadratic polynomial. So, so in this case, the problem would be if you are given a polynomial f which is approximately equal to a sum of powers of quadratics, can we recover each of those summands? And it turns out that this is the scenario which is applicable to learning mixtures of Gaussians, because the summands sort of capture the true moments of one component of a Gaussian mixture, and the sum is because you have several components in our mixture distribution, and there is noise, or we know the polynomial the polynomial with the small formula only approximately, because the empirical moments that is what we compute from the sample, they are only approximately equal to the true moments of the distribution. So this P, which is, we call it the perturbation or the noise, this is because there's a gap between the sample moment and the true moment of the distribution. So here's our problem. Given a multivariate polynomial which is approximately equal, or it's equal to a sum of simple polynomials plus a small perturbation P, we want to recover the summands SIs approximately. And P is small, again in the sense that if you have to think of P as a vector, then it has small norm. Yeah. So now, as I've indicated already, I've changed my viewpoint about polynomials. Earlier, I started out thinking of polynomials as just bookkeeping devices for keeping track of the moments of a distribution. Then in the second part, I changed my viewpoint about polynomials as functions, which given an input produces an output. Now I will change my viewpoint about polynomials yet again. I'll start thinking of them as vectors here. And so let me give you a quick overview of lower bounds. So the lower bound problem is the following. We want to find explicit polynomials f such that if you write it as a sum of simple polynomials, the number of summands R has to be very large. So for example, I want to say that if I write a Hamiltonian polynomial as a sum of powers of quadratics, then the number of quadratics that I will have to pick is going to be extremely large. So that's the nature of the problem. So it turns out that pretty much all the lower bound proofs, they follow this template. We construct somehow a space of linear maps. So these linear maps, each of these linear maps L, they act on the vector space of polynomials. Usually we want to look at the vector space of polynomials of a specific degree, D. Let's say degree 10. Right? And then these linear maps, they will take as input a polynomial thought of as a vector and output another vector. And typically this other vector space where you map them to, typically this will also be some vector space of polynomials, maybe of a different degree. Maybe let's say degree 8. So we want this collection of maps to have the following two properties. that if you take a simple polynomial, like again, for example, a power of a quadratic, and hit this simple polynomial with this collection of maps, so you get a collection of points in the space, vector space W. So you take these points in W, look at the subspace in W spanned by all these points. And we want that the dimension of this subspace spanned by the image of Si, of any summand Si, under this collection, it should be small. And what I also want is that if you take the polynomial f, the hard polynomial f, and hit it with this collection of linear maps, the dimension of the space spanned by the output point should be large. And this is the sort of the complexity measure which Newton was referring to yesterday, which given this collection of linear maps, if this collection has this property, then this dimension of the space spanned by the outputs, this is some measure of the complexity or the hardness of this polynomial. So what I want, okay, here's a exercise which I leave it to you, that suppose that if I could construct some such collection of maps, let's say for, again, the summands being, let's say, powers of quadratic polynomials, then you can verify that this will give you a way to lower bound the number of summands. In fact, the ratio of the second quantity, the second dimension to the first dimension, that ratio will be a lower bound on the number of summands. And that's just essentially because of linearity. So yeah, we in the algebraic complexity community have spent a lot of time trying to discover such collections of maps, and proving bounds on these dimensions, which will give us a lower bound. So now let me tell you that assuming we have such a collection of linear maps, how you can use it to do the reconstruction problem or the learning problem. So let me state the learning problem first. We are given as input a polynomial of degree d, and suppose that, for simplicity now, there's no noise, and suppose that it's a sum of a small number of simple polynomials. We want to output these summands, right? And yeah, in applications in unsupervised learning, these summands sort of capture the components of some distribution. So we take this collection of linear maps L given to us by the lower bound proof, and we will use another collection of linear maps. Typically, this other collection M is also inspired by the collections which occur in lower bound proofs. So what we'll do is we'll hit, and the example to keep in mind throughout this part of the talk is the example where the summands are powers of quadratics. And in this case, the output space will be polynomials of somewhat smaller degree, d minus k, and the collection of linear maps will be essentially kth order partial derivatives. So you can take a polynomial and take its derivative along a any particular direction, and partial derivatives with one additional operation, that you restrict, after taking partial derivatives, you restrict my collection of polynomials to a low dimensional subspace. Let me not go into the details, and M will be what we call partials composed with multiplications, degree 1 multiplications. So it's not very important at this point what exactly these maps are. I just wanted to give you a flavor of the kind of maps that we use. So we take such a collection of linear maps and hit my given polynomial f with it, and I look at the space spanned by the output points. So let's call this space U. And then something like typically something interesting happens, that this space U is a direct sum of the spaces that you would get if you were to hit each summand with this collection of linear maps. So direct sum for vector spaces is sort of the vector space analog of saying that some set is a disjoint union of subsets. So that's sort of the vector space analog, that this space U is in some sense a disjoint union. Formally we call it a direct sum of these subspaces corresponding to each summand. So like the containment in of the left hand side for the first property, the containment of the left hand side in the sum of the right hand side vector spaces, that's clear from linearity. What is interesting is that these sums are in fact direct sums, and this containment is in fact an equality. And I'm slightly simplifying here. The other collection of linear maps will have this property that each of these subspaces will be invariant under the action of this other collection. So every map in this other collection M will map one of these subspaces, any of these subspaces LSI, to itself. So we call this phenomena the blessing of dimensionality, because it tends to be true when you have points or polynomials in large dimensional space. And it is also somewhat counterintuitive. Typically, dimensionality tends to hurt us algorithmically. As the dimensional increases, the dimensionality of the input increases, it becomes more and more difficult to design algorithms. But here it's just the opposite. The dimensionality actually helps us under certain non-degeneracy conditions. So then I use these, so we sort of find the common eigenspaces of U under this collection of maps M, and these eigenspaces are precisely the image of every summand. So U1 will be the image of S1 under the operators L, and then there's some simple, relatively straightforward linear algebra you can do to say that given the image of S1 under L, you can recover S1 itself, and similarly you can recover S2 and SR. So that's all that I will say about this learning algorithm. So initially we did this when there was no noise, and then we looked at the same problem and essentially made this algorithm robust to the presence of noise. Uh, so the noise is captured in this vector P of the perturbation vector P, and the bound that we got for how far away. So when there is noise, you cannot hope your outputs to be exactly equal to the unknown SIs. What you can hope is that the output will be close. The S1, S2, SR that will output will be close to the true SIs. So we want to bound how far away the output can be from the true answer. And this bound that we get involves this is in terms of singular values of certain matrices. And you can imagine that these collections of operators will correspond to some matrices, and so the bounds are in terms of singular values, or more specifically the minimum singular values of certain matrices. And we had no clue how to how to prove these singular value bounds. But we made this optimistic conjecture that the singular values are, if you take even a worst case instance and you slightly perturb that worst case instance, then these singular values are not too small. So if this conjecture was true, it would imply efficient, what we call smoothed algorithms for many of these problems, including mixtures of Gaussians. And as I mentioned in the beginning, very recently this was proved. Again, there's a slight gap here, but essentially it was proved by these folks, and there was also some important work in between by Bafna, Kothari, Zhu, and I forgot the other authors, but there was a sequence of works, and this latest work essentially proves this conjecture. So that gives us algorithms with some provable guarantees about this some of these problems. So let me just any questions? So let me just end with again this problem that I started out with. So unfortunately this so essentially, can we build a system which can understand our world, in the sense that it gets as input humongous amounts of images, videos, maybe audio and language data, and can it use that to essentially understand our world? We don't know. We feel we have some way to approach this problem, but and that's what I've been working on. Thank you.
Thank you. Are there any questions?
Hi, sir. So, is there any gap between that empirical moments and original moments? What is that gap?
So, the gap. So take this example. Suppose you have. So think of the heights of people in India, right? So roughly the heights of people in a region, they will follow, let's say, approximately a Gaussian distribution. But you have like 1 billion people in India. You can't measure all their heights. You take a sample of, let's say, 1,000 people, and you want to. So if if this assumption was correct, that for all the billion people, the distribution of heights of the billion people is a mixture, is a Gaussian, or is a mixture of a small number of Gaussians, then using a relatively small sample of size 1000, you could hope to recover what is the average height, the mean of the distribution, and what is the variance, like roughly what is the height, the bounds, such that let's say 65% of the people in India are within this bound, right? So when you sample, let's say, the heights of 1000 people, the average height that you take of these 1000 people, that will be close to, but not exactly equal to, the true average height of the billion people, right? So that's why this error comes. This, what we are calling error or noise. That's the source of it.
So what is that error exactly? So that is what I'm asking. So there is a gap between that true height and this empirical height, right?
Right.
So what is that gap?
So yeah, that what we know is that are bounds on that gap. So I'm not sure is that like what we know is that the magnitude of this gap will depend on how many samples that you pick. If you pick 1000 samples, you will get a larger gap. If you pick 10,000 samples, the gap between the true average and the sample average will be smaller. And what we also know is typically this will fall off as square root of the number of samples, the gap. So the larger, the better, but the way it falls off is the square root of the number of samples.
Thanks for the talk. I did not understand all the math, but the broader connection was very interesting to me. So I just wanted to ask you, that is, we are talking a lot about this explainability in the decision. So will this kind of, if your conjecture and all this is working, so can we believe our decisions much more, will it be more robust in that angle? Can you comment on that?
Yeah. So yes, so let me just give the context for this question. So there has already been tremendous progress in doing unsupervised learning on languages you must have heard of, GPT-4, and on other modalities like vision and video also. So there are these what are called diffusion models for understanding images, and yeah, some of those outputs are incredible, and but still, in some sense, or kind of, we have trained these models, and they kind of understand, let's say, our corpus of real-world images, but we train them using what are these called these transformer networks. So they understand the real world to some extent, but we don't understand what they understand. And if we succeed with this, it will be a much better situation. So in particular, we will be able to interpret what we have learned also.
Thank you.
Any other questions?
Thank you, sir, for the talk. I was wondering if you could just re-explain the exact, or rather the maps that were used for the mixing of Gaussian example we discussed.
Yeah. So
Yes.
yeah. So in this case, think of k as, let's say, 2 to be like to be concrete. So here are what to do. On polynomials, you take derivatives. So derivatives are linear operators on polynomials. So if you take a polynomial of degree d and take its derivative with respect to, let's say, x1, the variable x1, you get a polynomial of degree d minus 1. And also it has this property that the derivative of a linear combination, let's say f1 plus f2, is that linear combination of the derivatives. So the derivative of f1 plus f2 is derivative of f1 plus derivative of f2. So you use derivatives, higher order derivatives, let's kth order derivatives, and think of k as 2, for example. And then you do one more linear map. You take some of the variables, let's say the last 20 variables, and you set them to the value 0. We call it projection. And essentially this is also a linear map. So if you take a sum of two polynomials f1 and f2, and in the sum if you put, let's say, the last 20 variables to 0, that's the same as taking each of those polynomials, putting the last 20 variables to 0 and then adding them up. So this is also a linear map. And the first collection of linear maps, L, is a composition of these two things. And the second collection of linear maps that we use, you can use other collections also, but yeah, this has the cleanest sort of proof. So we take derivatives again, this time only first order derivatives, and then you have another collection which corresponds to multiplying a polynomial with a fixed polynomial, say y1. So does that answer your question?
Yes, sir. Thank you.
We'll take one last question.
Hi, I'm Dhanajit from IIT Kanpur. So I have a question about that. In unsupervised learning, we have this assumption about the inputs coming from a distribution, right? So will these results still hold in the case that the input distributions are changing over time?
Yeah. So these particular results, no, or okay. Let me put it this way, that in the very beginning I roughly said that sort of real world data sets have some structural parts to it and some random part to it. So the random part corresponds to distributions, and if the distribution changes and we train our model on a particular data from a particular distribution and the distribution changes, our model often runs into trouble, right? So like the results here also which pertain to some of the results here also which pertain to distributions, that will not hold. And in general, in unsupervised learning and machine learning, that's a problem, but not in some sense not the structural parts of it. So so again, take this just to sort of give you some sort of flavor of what I mean by that. So imagine your data is like this, right? So there are structurally there are these three lines on which my data points lie, and on these lines themselves there is some unknown distribution of points. Now typically, like in real world, we don't expect the structural things to change. So it, like, even if you take images from some other distribution, like imagine taking images where earlier you were taking images, mostly outdoor images, let's say, right? And you gave me a bunch of like images of outdoor things, trees, mountains, clouds, and things like that. And I see that, and I understand something about the world from it. And now you come and give me a data set of indoor photos, like auditorium and offices and things like that. So a large part of what I have understood about the world from those outdoor photos will no longer hold. But if I have discovered structural things like what are interiors of objects, what are boundaries of objects, what kind of boundaries occur, what kind of shapes occur, maybe some of what kind of textures also occur, maybe it's, so those kind of things might still continue to hold.
Discussion. Let's join me in thanking Neeraj once again.
Thank you.
And as a token of appreciation from the ARCS organizers, there is a memento to be given, which is not a physical object. I call upon Venkatesh Raman to present it.
Yes.
So this is the ACM India initiative to plant trees in the names of people. So this is a tree which has been planted, and Neeraj now has the code so he can track the growth of
Thank
this
you.
tree.
Yeah, awesome. Thank you.
So this is